In this video, we're going to explore the Schrödinger equation. We're going to do a heuristic derivation. This will show us where the equation comes from, but it also will introduce us to its use. As we'll see, good old Erwin, he developed two forms of his equation, a time-dependent and a time-independent form. The Schrödinger equation allows us to determine the wave function of the system. That's important because the wave function provides a complete description of the system, and we can find that wave function by application of the Hamiltonian operator. Now, this statement leads to several questions. What's a wave function? What's the Schrödinger equation? And what's an operator? And these questions we're going to answer in this video. So let's take a look at postulate 5, the unitarity postulate. It says that for every physical system, there corresponds a unique operator representing the total energy of the system. This is so important as an operator that we'll give it a special name, the Hamiltonian, and the observable physical states of the system are described by those wave functions that satisfy the time-dependent Schrödinger equation. Oh, there it is. So let's see if we can derive this equation, the time-dependent Schrödinger equation, for a simple case. A simple case is that of a free particle. Free particle, no potential energy in this system, and its wave function is given here. Psi of spatial coordinates and time coordinates is just a normalization constant times an exponential function, I times the quantity k, x minus omega t. K is the wave vector, omega is the angular frequency. De Broglie formula related the linear momentum to wavelength, which for a free particle we'll find is equal to k times h bar. We can also use the Planck-Einstein relationship of quantization of photon energy, right? That the energy is related to h bar omega. So let's substitute these two in here so that we get a new version of the wave function now is expressed in terms of the linear momentum and the total energy of the system. Those are two properties that we would associate with particles, so this is the natural way to express the wave function for a free particle. Remember, as always, for all systems, the total energy is kinetic energy plus the potential energy. But right now we have a free particle, so the potential energy is equal to 0. Therefore, the total energy is just the kinetic energy. So we've got a way to express the wave function of the system. Now let's do a bit of calculus. First, we're going to take a derivative with respect to time, the first derivative with respect to time. So we do that, we throw this in Mathematica, we get an answer, and find an easy answer. The first derivative of the wave function with respect to time is I over h bar times E, the total energy of the system, times the initial wave function. Now let's take the second derivative with respect to the spatial coordinate x squared. Again, take the derivative, do a little algebra, and we'll sort out, oh yeah, again, the original wave function is in there times, this time, minus p squared over h bar squared. Do a little bit of algebra with those two derivatives, and we can easily show then that I h bar times the first derivative of the wave function with respect to time is equal to minus h bar squared over 2m, the second derivative with respect to x squared. This is the time-dependent Schrödinger equation for the free particle and is completely compatible with classical physics, where energy of a particle would be equal to its linear momentum squared divided by 2p. This term over here is associated with the kinetic energy, which is the total energy in this case of a free particle, and that it provides us a way to determine the kinetic energy operator, which we'll call T hat. T hat, the kinetic energy operator, is just minus h bar squared over 2m times the second derivative with respect to the spatial coordinate x. We've found a way to determine what operator should be. using this derivation, right? And if we were to look at a system where we did have a potential, right, then the Hamiltonian would be the kinetic energy operator, which always looks something like this, depending on the coordinates we have in the system, and a potential energy operator. And the potential energy operator is where all the interactions are, right? If we use that general form of the Hamiltonian, then we'll get a general form of the time-dependent Schrödinger equation shown here, with one term for the kinetic energy, another term for the potential energy. The sum of those two is equal to I h bar times the first derivative with respect to time. So this time-dependent wave function, capital psi of x and t, it is the solution to the time-dependent Schrödinger equation. More importantly, if this potential over here is independent of time, that will allow us to factor the wave function itself, that time-dependent wave function can be factored as a spatial component times a temporal component. And this spatial component, right, the spatial part of the wave function, it describes the stationary states of the system. The absolute square of the time-dependent wave function is equal to the absolute square of the time-independent wave function. So that's why we call them the stationary states. Psi of x, the probability distributions that you get from psi of x are not time-dependent. Therefore, they describe stationary states of the system. And therefore, we can also write a time-independent Schrödinger equation that is minus h bar over 2m, second derivative with respect to x, plus the potential times the wave function is equal to the energy times our wave function. Now we can write the time-independent Schrödinger equation in a very compact form. If we recognize again that the Hamiltonian is the total energy operator, kinetic energy plus potential energy, then we see we can write the time-independent Schrödinger equation as simply the Hamiltonian h hat operating on the wave function psi is equal to the energy, a constant, times the original wave function psi. All of chemistry and physics is contained within this equation. The Hamiltonian describes all the interactions in the system. The wave function describes the system itself. So we just need to write down a complete Hamiltonian that describes all the interactions, and then we'll be able to find the wave functions. But that potential energy term requires a detailed knowledge and a proper mathematical expression for every kind of interaction that's in the system that's important to it, whether that's electrostatics, van der Waals, gravity, whatever. Because of this, one, it's hard to construct the right Hamiltonian. Two, it's not easy to find the wave function. And what we'll find out is that the Schrödinger equation cannot be solved exactly for any atom or molecule containing more than one electron. And therefore, the development of approximate methods is extremely important. So, to summarize, the Schrödinger equation can be written in time-dependent or time-independent forms. It's the time-independent form that we will concentrate on most of all. The wave function here, psi of x, in this case, that is a complete description of the system. The wave function is found by solving this time-independent Schrödinger equation. The correct wave function requires the correct Hamiltonian. It's not easy to develop both of those non-trivial exercise. Therefore, the development of approximate methods will be critical in our further investigations of quantum chemistry.